Next type of graph we're going to look at is absolute values. Now we've looked at the most basic of absolute values. Let's look at it in a little bit more detail. If we have to draw y equals the absolute value of function x, so far we've really only looked at linear functions, but it could be anything. It involves symmetry in the x-axis. Now that doesn't mean the final picture is going to be symmetric in the axis. What I mean by that is we're going to get the bit that's below the x-axis and reflect it above. So that's what I mean by symmetry, that reflection in there. So here's random curve. If I wanted to find the absolute value of x, then whatever is below disappears and gets reflected above. So that would be y equals the absolute value of function x. But we could also have function absolute value of x. This also involves symmetry, but now it's in the y-axis instead of the x-axis. We're going to reflect the positive part over into the negatives. So similar to what we just did, but now it's the left-hand side that disappears rather than the below. Basically the negatives are disappearing. And we reflect over, and there's function absolute value x. What about if it's y we're finding the absolute value of? What does that do? This one will also have symmetry in the x-axis, but now we're going to reflect the part of the function which is positive in the x-axis. What do I mean by that? Is our original graph. Below disappears once again. But this time, instead of reflecting below above, we reflect above below. So that is absolute value of y is equal to function x. What about if we found the absolute value of both of them? Well, it has symmetry in both axes. What ends up happening here is whatever's in the first quadrant gets reflected into every quadrant. Once again, here's random curve. We get rid of everything but the first quadrant, and it gets reflected into all four. Both the x and the y have absolute values. Okay, let's go crazy. Y equals the absolute value of function absolute value x. Well, now we're pretty much doing compound functions, because we can say we know how to find function absolute value x, and we know how to find absolute value of function x. We just can do it in two stages. So we'll end up with symmetry in the y-axis and reflection in the x-axis. As I say, we know how to find that one, function absolute value x. Now all we're really saying is find the absolute value of that, and our rule for that was whatever is below gets reflected above. How about absolute value of y is equal to the absolute value of function x? This one will have symmetry in the x-axis and reflection in the x-axis as well. There's the original graph. We could draw the absolute value of function x, but now we want to say, let's do the absolute value of y of that, which was whatever is above reflects below. We start getting some wonderful pictures. So that's all different variations of absolute values, what can happen to the curve. Square root graphs though. The graph of the square root of x. Again, first draw the original curve, function x, and we notice a few things. We know, for instance, that the square root of function x will only be defined if function x is positive. You can't find the square root of a negative number. But we also know that the answer, because we're talking about the positive square root, has to be greater than or equal to 0. Once again, here's random curve. The first thing I can say, if I'm going to find the square root of that, whatever is below disappears, so that bit goes and that bit goes. They're not in the domain anymore. So it's just this curve I'm applying it to. The stationary points will still be stationary points. Well, they're x values anyway. The y value will change because you're finding the square root of the y value. So I know this stationary point, this turning point here, will stay. Now, if I find the square root of a number bigger than 1, it's going to be smaller than 1, so that it must come down, must be below there. Discontinuities are going to remain for all the reasons we said before. If it's not in the domain of the original function, it can't be in the domain of the new function. But horizontal and oblique asymptotes may well change. Basically, find the square root of their value. So our graph has this horizontal asymptote. It's a number that's less than 1. If I find the square root of a number less than 1, it's going to get bigger. So it'll go up. It won't go more than 1, but it'll be above that one. Okay, so I know there's a horizontal asymptote there. If the value is greater than 1, that's what I'm saying, we know the number is going to get smaller. Okay, find the square root of a number bigger than 1, it gets smaller. Therefore, as far as the picture is concerned, the new graph will be below the original graph. But if it's less than 1, the new graph will be above the original graph. It's the opposite of what happens when we're squaring a graph, because it's the inverse operation. Okay, so what do I know here? Well, the square root of 1 is 1, so there's a good set of points to plot in. What we're saying is it will start above, because this is all less than 1. It'll hit 1, but then it will go below. Same idea, but the other way around to when we looked at the squaring graphs. Now, the actual x-intercepts really do require a bit more thought. Let's just have a look at this. So y is equal to x to some power, so a on b. And for example, I've used power of a third, 2/3, so cube roots basically. There's the two graphs, x to the power of a third, x to the power of 2/3. Things to note, this will always happen. If that power is less than 1, the curve will always be concave down in the first quadrant, thus creating a vertical tangent at the intercept. Parabola on its side, for instance, y equals the square root of x would be x to the half. Half is less than 1. We end up with a vertical tangent at that point. Now obviously 3 on 3, it's just power of 1, so we've got our straight line. But once it goes bigger than 1, now the curve goes concave up in the first quadrant. We get a horizontal tangent rather than a vertical tangent at those points. And so there's 4/3, 5/3 and 6/3 is our parabola, x squared. So let's just look at a few of these then. So if the original function is x to the power of 4, remember you're finding the square root of it. Well, there's the graph of the function. We know it's got that U shape, bit flatter at the base than a parabola, steeper at the sides. The square root then, well, we can just look at it and go, well, hang on, x to the power of 4, find the square root of that, well, it's x squared. So I end up with the parabola. Y squared equals function x is a variation of y equals function x, because what you're really now saying is you have both plus and minus the square root. So you get this reflection in the x-axis, you have both plus and minus. Now x cubed, there's our original function. The square root, okay, square root, the power is now 3 on 2. 3 on 2 is bigger than 1, so I get a concave up curve, like that. And if it was y squared equals function x, we get that interesting shape on its side. X squared, well, obviously our parabola, x squared, square root of x squared is x. So it's coming in like a straight line, because y equals x. And that's why we end up with a V shape, much like an absolute value. And y squared equals function x, you end up with a cross. X equals 5/3. That power is bigger than 1, so we see it's concave up. Square root of that, okay, square root of 5/3 would be 5/6. We're now talking about a power that's less than 1. The curve goes to concave down now with a vertical tangent. And then y squared equals function x, there's the reflection there. 4/3, there's the picture of 4/3. But find the square root of that, you get 2/3. 2/3 less than 1, we have a vertical tangent. So back to ours, we don't actually know what the power is. So we can make some guesses. It looks like it's a single root. So that's what I'm going to assume. Find the square root of a single root, power of 1, I get power of a half. So it's going to have that rounded shape. It's going to have a vertical tangent. Yeah, I got a little bit dodgy there with my drawing. And maybe I might have exaggerated my vertical tangent a bit over here. But that's what I'm trying to get at. It's a vertical tangent at that point, because it has over the original curve, goes through 1, then under. Over, under, over, and then our last bit, it's over with those vertical tangents. So there it is. Ooh, that's horrible, isn't it? But anyway, there's the idea of it. So that's y equals the square root of function x. Of course, if they asked us to do y squared equals function x, we would simply reflect it over. And that would be our shape for our random curve. Okay, that shall do us for today.